Last week we started a problem that we haven't finalized, and it was the problem of a polymer, right? So just remind you, that marker, problem of a polymer. Okay, what was the problem? We had a wall. Near the wall, we constructed a model of polymer that is based on single links that we termed monomers. Each link can be oriented either in direction of the y-axis, x-axis, minus x-axis, and minus y-axis. Okay. So in general, the polymer that we constructed looks like this. Now all the orientations are independent of their neighbors. At the end of the polymer there is a string that is connected to a pulley, and there is a mass on the string, and the size of this mass is m. So there is a force of mg pulling down on the polymer. After playing a little bit now, I just remind you that the energy of each and single link is going by epsilon up when it's oriented either in the y direction or the minus y direction. So the energy, if I'm going up, this has an energy of epsilon, this has an energy of epsilon, and if I'm oriented along the x direction, I have an energy of 0 and I have an energy of 0. Okay. And after we worked a little bit around it, we obtained the following expression for the total energy. So the total energy was Ny plus, which is the number of links, the monomers that are oriented in the positive y direction, multiplied by epsilon, plus Ny minus multiplied by epsilon. So this is all the energies due to the orientations of the different monomers. They are completely independent. So this is the term that comes from all the monomers that are sitting in the plus y direction or the minus y direction. There is no contribution, at least to this part, to the total, to the energy from all the monomers that are pointing over there or pointing over here. But there is additional term due to this mass over here. Right? This additional term was the total extension of the monomer. So if we set the potential energy of the mass at such a level to be 0, such that the whole potential energy is just the extension of the polymer, so let's call it Lx. Okay. So here we have an additional term which is just the potential term of the mass. So we have over here Lx, okay, multiplied by A. A is the size of each of the monomers. Multiplied by mg. So I'm sorry, it is Lx mg. And Lx is the total monomers that are pointing to the left minus the monomers that are pointing to the right, multiplied by the size of each monomer, which is A. This is Nx plus minus Nx minus multiplied by A. So what we notice when we write the energy like this, that it's not just the sum of the energies of all the different monomers. There is something else, and this something else contributes an additional term that also is dependent on the different orientations of the different monomers. Okay, so let's write it down. So E, it is ny plus multiplied by epsilon plus ny minus multiplied by epsilon minus nx plus multiplied by mga minus plus nx minus multiplied by mg. So this is the total energy. Now remember, the trick is always to represent the energy as a sum of the energies of the different particles, okay? And we also need that the different particles won't depend on each other. Meaning, when one of the particles is in state with energy whatever epsilon, it's not affecting the choice of any of the other particles. Okay? So independence is crucial, and additivity for the energy is also crucial. So when we look on this specific expression, this energy, okay, we need to follow the prescription. We need to represent the whole system as a sum of independent particles with some specific energies. Now, we cannot use it when we're just we cannot apply this prescription when we're simply using the epsilon energies of the particles. Okay? It won't work. Can you close the window, please? Thanks. It won't work. Why it won't work? Well, because of the additional term over here. So what we do the following thing. We will say that instead of this representation of the particle, what we have is an alternative representation. So I'm inventing a quasi-particle, an effective particle, okay? And for this effective particle, the energies are different. For this effective particle, so it, again, effective particle. For this effective particle, the energies are different. So if it's pointing in the y-hat direction, it will have energy of epsilon. So all particles that are pointing in the upward direction, contributing epsilon, and this is the term over here. Okay. The same goes for the particles that are pointing in the minus y direction. They are also contributing epsilon, as we see from this term over here. Okay. Now, some of the particles are pointing to the left, or your right, all right? Now, I need them to contribute something. I see that all the particles, so I see this contribution over here. It is nx plus minus mga. I'm saying, well, I will take any particle that is pointing in the x-hat direction, and I will assign it an energy of minus mga. Right? So I have a particle that's pointing to the right, and it will have an energy of minus mga. Now I'm going to the last contribution, so of all the particles that are contributing to the left, okay, and I see that all the particles that are contributing to the left, their total contribution is nx minus mga. So I assign to each particle that is pointing to the left energy of mga. So instead of taking the regular representation of a particle with just two energies, 0 and epsilon, I'm saying I have effective particles, and those effective particles have 4 different orientations, and the energies that are associated with each of the orientations are like this and not like that. It's not that this is not true. This is perfectly true. But in order for my prescription to work, I need to invent new particles. For those new particles, the energy is exactly the same, right? So if I want the total energy of the system, I just go over each particle and I see at which state the particle is, and I sum up all the different energies and I will get this expression. So the additivity works and the energetic representation also works. Now, by construction, all those particles are independent. Okay? So the second condition also works. So I have additivity property and I have independence of the different particles. I can apply my prescription for canonical ensemble. Okay? And the prescription goes like, if you want to compute the partition function, all the particles here are identical. Calculate the partition function of one single monomer, effective particle, this one, not that one, this one, and take the power of n out of it. Okay? That's it. We don't need to assume how many states there are for all the different systems. There are a huge number of states. We don't care. We only care about one single particle with those effective states, energetic states. So what is Z1? Z1, it is, we sum up over all the different states, right? So it is I, E minus beta, EI. Where the I over here are the different energetic levels of one single effective particle. So what we have over here, it is e to the power minus beta epsilon. This is this orientation. So this is particles that are pointing in the plus y direction. Plus e to the power minus beta epsilon. Those are the particle state that is associated with the monomer going in the downward direction. Plus e to the power minus beta minus mga. This is the contribution of the state that is pointing to the right. And plus e to the power minus beta mga. This is the part that associated with the state that is pointing to the left. Okay, so we obtain that Z1 is just the sum. So Z equals to 2 to the power e minus beta epsilon plus e to the power minus or plus beta mga minus e to the power minus beta mga plus to the power n. And if you want to find anything that is related to some thermodynamical quantities, we know that the free energy is 1 minus 1 over beta log of z. And that's it. Okay. So the whole trick, the whole difficulty of this assignment was to write down the energy and from this exact expression of the energy decide, well, I have only one way to go. Okay. There is only one way to go, and this one way is to represent this expression over here in terms of independent effective particles. Sum of energies of independent effective particles. We had no other way to go but this. Okay. But the moment that you recognize this, all the other tricks, this factorization of the partition function, etc., 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 it comes into play and everything becomes extremely easy. What we will do from now on, from many different models, is this step. We will write down the energy and somehow we will manage to represent everything in terms of effective independent particles. Maybe by the end of the semester we will come to the other tricks that we know in physics, how to deal a little bit differently with systems where you cannot do this representation by independent particles. So there are systems, specifically systems that are near critical phase transition, that this won't work. For any other system, you can always somehow represent everything in terms of independent particles. Those particles cannot be, maybe they're not going to be particles, maybe they are going to be very crazy creatures. Okay? but the idea is always going to be the same. But sometimes it won't work, and we will see, well, if we'll have time, we'll see how we manage with that.
Stas?
Yes?
How can you, for example, find the generalized force from this equation?
Great! So how can I find the generalized force from this equation? So I know, this is my next question. So let me continue, and I hope it will be a little bit more clear. So the next step that I want to address is how exactly, or what exactly I do with this expression over here. So, yes? So the question is, why do I have a minus sign over here? Okay, so the potential energy, I assign it that it's 0 when Lx is 0. Okay, so this is my 0 level. And then the mg goes down, so the potential energy is going to be negative. All right? So the question is how an x and an y and whatever is dependent on mg. You don't need to know this. It's going to be a statistical problem. You'll see in a second, okay, how I determine different nx's and ny's. But in general, I have a probability representation of the nx and ny. The only thing that I care about is that the total number is n. And that's it. I know that ny plus ny minus plus nx plus nx minus equals to n. That's the only thing that I know. So if I put mg, there is going to be not enough molecules that it will work, but it will always work. It's just Lx going to be different. Lx, it's a random variable. At one point of time, it will be 0. In another point of time, it's going to be tremendous. There is a probability function that describes Lx. And I can find it if I want. Yes, sure. You remember, so Lx is fluctuating, as any other observable in the system. If I look on Lx, this is my t. If I look on Lx as a function of time, okay, it won't be constant. Okay. It will fluctuate around some specific value, like this. And this is what I will observe in an experiment. And this dashed line is the average quantity. So I can find the average quantity of Lx. And this is what comes into the, and this was your question, this is what comes into the thermodynamical description on the average quantities. But in experiment, remember how I started this problem. Problem is that if you go to the nanocenter over here, you'll see experiments exactly like that. They take a polymer, they put a golden particle on one part of it, they connect the polymer to a glass usually, and they start to pull this golden particle. Okay? And the position of this golden particle is fluctuating like this. Why is fluctuating? Because of all of what we have described already. Okay? Yes?
If the quasi-particles are identical, why don't you divide by n factorial?
Why do I have to divide by n factorial?
That we were told in the tutorial that if the particles are identical, you need to divide by n.
So you should ask them, do I have to divide by n factorial? Why do I have to divide by n factorial? What is the reason to divide something by n factorial? We will go to the Gibbs paradox later. But if you look on this, I have absolutely no reason to divide anything by n factorial right now. Specifically, the next question will be, well, if I know that this is particle, effective particle Moshe, and this is effective particle Reuven, and I will give name to all my particles. They are all different. Why should I divide by n factorial? We will come to the Gibbs paradox a little bit later. But now, well, at least I haven't told you, there is absolutely no reason to divide by anything yet. Any other questions? Yes.
אתה יכול לחזור על ההסבר למה יש מינוס באנרגיה של
So if the question again, why do I have a minus over here? So let's assume that this is my energy 0. And I put here my mg. So the potential energy of my mass is 0. I go down Lx. Okay? What's going to be the potential energy of the mass over here? Minus Lx multiplied by mg. Okay? Because I set my 0 energy level at the point where Lx is 0. Yeah, but what is this length? What is this length? What is this length? This is exactly by how much it's moved. So think about it. It's all those problems in mechanics. You have a string of effectively one length, and you go up or you go down.
כן, אבל ככה אני מבין את זה, ובמערכת שלנו אני לא כל כך מבין. כי גם נגיד, אם כל הפולימרים מצביעים ימינה, אז האנרגיה תהיה חיובית, ואם כל הפולימרים מצביעים שמאלה, האנרגיה תהיה שלילית.
Right. So what's the problem?
שכאילו, האנרגיה של הפולימרים זהה
No. It depends on the mass. Mass is part of my problem, right? It's part of my problem. So mass goes up, or mass goes down. It affects the energy of the system. I cannot neglect it. I cannot look on the polymers completely disconnected from the mass. I cannot do this, right? So if you're trying to do this, this is a mistake, because the system now includes polymer plus mass. It's not my system is polymer and mass is the outside world. No, this is your system. Okay? So this is the total energy is going down. All right. So this brings me to the next question, which related to several of the questions that were asked over here. Because eventually I want to measure something. My measurements are going usually depend on some thermodynamical quantities that I will obtain from this equation over here. Okay, I have a free energy, and you had a class on thermodynamics, so you know that we can take many derivatives of this quantity and obtain whatever you want, right? Whatever you want, you can obtain the moment that you have a state equation relating to energy or relating to free energy. And what I want, or the experimentalist want to measure, is the elastic modulus. Okay, so what's the idea? The idea is as follows. Let's assume that I have a wall, and there is a spring that is connected to this wall. There is a mass, and I pull on this mass with a force F. So I know that the extension Lx minus, this is Lx, somewhere over here going to be L0. So I know that Lx minus L0, okay, would be equal to K multiplied by F, where K is a spring constant. 1 over K is the elastic modulus. Okay. So let's assume that I'm experimentalist, and well, I want to learn some of the properties of this polymer. And the thing that I have in mind is, again, I connected my polymer to a wall. Okay. So there's a wall. There is a polymer, which is complicated. There is golden particle. And I somehow pull this particle. Okay. Now from this experiment, for example, I can obtain the elastic modulus, or the spring constant, of my polymer. Okay? I can understand that the different types of molecules provide different elastic moduluses. Okay? Different types of springs have different spring constants. Exactly the same I can obtain for a real system, which is not a spring, but still have to be somewhat elastic. Right? So I want to try and explore those elastic properties So what do? Well, I have now the free energy. Okay. I know what my force is. My force is mg. Okay. Let's try and extract the elastic modulus out of the system. Okay. So the question is clear. I have the free energy. It's over here. And from this free energy, I need to extract information, useful information, and the elastic modulus is this is the information that I want to extract. How do I operate? How do I operate in thermodynamics? In thermodynamics, which is quite easy to apply because you just need to know what's the kind of derivative you have to take. Okay. In thermodynamics, let's assume that you have F. Okay. And if you now want to obtain some knowledge about the behavior of F, you write down that dF, okay, equals to minus S dt plus, it's going to be tau dL. So you have a connection between the different derivatives of your free energy and the length of the system to the tension in the system. And in our case, this tension is going to be mg. Okay. And then you take a bunch of derivatives and you work hard, hoping that you will get somewhere. Okay. This is not the approach. So you can do this, okay? And it's a very natural way, classic way of doing things. But the way of statistical physics is somewhat different. The moment that you know, something about probabilities, all right, you can forget completely all those representations of free energy, etc., 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 and you can operate with probabilities alone. So what do I mean by that? So instead of taking different derivatives, okay, I will say what actually do I need? What do I actually need? Okay, so what I need is the representation of my length and the connection between this length to the external force. Now, what is the length of the system? What is Lx? So Lx, I only care about the particles that are pointing to the left and to the particles that are going to the right. Okay, so Lx is going to be nx plus minus nx minus multiplied by 8. Okay. And there is a wonderful law that you all been taught in probability 101. Okay, so Lx is a fluctuating quantity. Eventually in experiments, I will measure something about the averages. All right. So I need to learn not what are the fluctuations, but what is the behavior of the average. And the average, it's always easy to find since you all been taught in probability 101 that the probability of a sum, it's a sum of the probabilities. So Lx average is the average of nx plus minus nx minus a, right? So this is a random variable, this is a random variable, and this is a. We can take a out, and here we are going to have nx plus minus nx minus average. So we need to compute nx plus, and we need to compute nx minus. How do we compute those guys? Okay. So let's look what happens to nx plus. So we go for each and single particle, and we only take contributions when this particle is pointing to the left. If the particle is pointing to the upwards or downwards or to the right, okay, we do not count it as nx plus. So nx plus is what? Let's take an indicator function of each particle. So I'm sorry. So nx plus is x, how I will write it down? I will write it down as follows. So for each particle, let's take particle number I. Okay. Particle number I. Okay. For each particle, I have the following. F of I, it is 0 if particle number I is not pointing in the x direction. 1 otherwise. Okay. So nx plus is just the sum over I, f of I. Right? I just need to count all the particles that are pointing in the right direction. Right? I go over each particle in those bunch of monomers, and I ask each of them, are you pointing to the right or not? Are you pointing to the right or not? If it's pointing to the right, I count it as 1. If it's not pointing to the right, I count it as 0. And in the total, nx plus is just this sum. Okay. Now, and this is the nice things about probabilities, is that if I want to compute nx plus, is just the average. It's just the average of a sum over fi average. An average of a sum, it's always a sum over averages. So it's just a summation of the average over fi. Now, since all the particles are identical in their properties, fi, or average fi, is going to be exactly the same for the first particle and the second particle, and the third particle, and etc., etc., etc. So this is simply n, because I'm counting over all different particles that I have inside my system, f1. Okay. Now, what is f1? No.
1 times the e to the power of minus beta divided by the rotation.
There is a function. There is a way to calculate probabilities, right? So we know that f1, or probability of f1, probability of f1. Okay. So before that, f1 average is just 1 multiplied by the probability of pointing to the right plus 0 multiplied probability of pointing not to the right. Not to the right direction. Okay. I just have two options. It's like a Bernoulli trial. It's either 1, either 0. The average is the actual value. It's 1 multiplied by probability. Because why it's 1? Because I find it. And 0 because it's the value when it's not pointing to the right. Okay? So f of 1, it's 1 multiplied. What is the probability of pointing to the right? So this is, the probabilities is e to the minus beta energy of this state. What is the energy of the pointing to the right? Minus mga. So here I'm going to have beta mga divided, I'm looking on one single particle, and I know the probabilities. The probabilities are e to the minus beta, the energy, divided the partition function of this single particle, divided by z1. Okay? So this is f1. So I know that nx plus average, it is n multiplied by e to the power beta mga divided by z1. Let's do the same thing for nx minus. Okay. For nx minus, let's define g of I. The g of I is 0, not pointing to the left, 1 pointing to the left. Nx minus equals to the sum over all the different monomers of g of I. I do exactly the same, I'm just changing the notations over here. That's it. So nx minus average is just the average of the sum of g of I. The sum of the average of a sum, it's always the sum of the averages. The most important thing that you have to learn in probability. So it is the sum over I over summation of g of I. I'm saying that all the statistical properties of all the monomers are exactly the same. This is how I created them. So this is simply Ng1. Now, as I calculated the average F1, I'm doing exactly the same for G1. So G1 average, it is 1 multiplied probability to point to the left plus 0 multiplied by something, and I don't really care what this something is because it's multiplied by 0. I have only two states, 1 or 0. This is the magic of Bernoulli trials. Okay, so what I'm getting, that G1, it is, again, like here, I take the exponent minus beta the energy of pointing to the left is mga, so here I'm going to have minus beta mga divided by z1. Okay, so nx minus average, it is n multiplied by e to the power minus beta mga divided by z1. So I have nx plus and I have nx minus. And remember, that Lx average equals to A multiplied by Nx plus minus Nx minus, and equals to A multiplied by N divided by Z1. And here I'm going to have e to the power beta mga plus, minus e to the power minus beta mga. This is the average extension of the spring, or the polymer in our case. Now, we don't have a lot of time, But what was the original question? Remember, I had Lx minus some L0 equals to K multiplied by mg. Right? I take a force, exert a force of the size over mg. Somehow the polymer extracts, have an extension, all right? And in general, it's going to be fluctuating. Okay? So I'm taking all of this, the averages of the left-hand side and the right-hand side. I have Lx minus the average L0, which is constant, equals to, all here are constant quantities. So it is K multiplied by mg. I remind you that the quantity that I want to calculate is this K over here. Okay? So what do I do in order to find K? I'll take derivatives with respect to mg of the left-hand side and of the right-hand side. So d over Lx over dmg minus d over dmg over L0 equals to d with respect to dmg over kmg. Why I have done this? Because when I take the derivative with respect to a constant multiplied by something, and if I take the derivative of all of this with respect to this something, in my case it's mg, I'm left only with this constant.
Stas, why not simply divide by mg?
I can divide by mg, but I don't know what L0 is.
Okay.
Right? L0. So if you have a simple spring, you can say, well, let's forget about this L0. I can measure it, but if I cannot measure it, right? So I don't need to go and say mg equals 0 in order to find L0. If I don't want to not exert a force at all, and I don't want to go and calculate what is this L0 over here, I know it's not dependent on mg, right? So when I'm taking derivatives, this is simply 0. Right? So what I have is that d with respect to mg over Lx average equals to k. Now usually what is calculated is kappa, elastic modulus, which is 1 over k. Okay. Then we'll finish this exercise tomorrow. But the only thing that we left with is actually to take those derivatives. Now, I don't want to go and take unknown derivatives with respect to thermodynamic quantities. When I have statistical mechanics prescription, I operate on probabilities. And because all the different particles are independent, this trick that I've described to you over here will always work. Why? Because average, it's always an average of a sum, because all the particles are independent. And then it's just a summation of different probabilities or different averages. We'll see how it ends tomorrow. Thank you. כן.
זה שלא כל אחד מקבל הסתברות, כאילו הסתברות של רבע בכל אחד מהמצבים.
כן.
מה זה אומר?
כי ההסתברויות, כי יש לך ההסתברויות מוגדרות על ידי אנרגיות. האנרגיות בכל מצב לא שוות, ולכן גם ההסתברויות לא שוות. תסתכל, ההסתברות בכל מצב